Chapter 3, Writing ROS Programs. In which we write ROS programs to publish and subscribe to messages. So far, we've introduced a few ROS features, including packages, nodes, topics, and messages. We've also spent a bit of time exploring some existing software built on those features. Now it's finally time to begin creating your own ROS programs. This chapter describes how to set up a development workspace and shows 3 short programs, including the standard Hello World example and 2 that show how to publish and subscribe to messages. Creating a workspace and package. We saw in section 2.4 that all ROS software, including software we create, is organized into packages. Before we write any programs, the first steps are to create a workspace to hold our packages and to create the package itself. Creating a workspace. Packages that you create should live together in a directory called a workspace. For example, the author's workspace is a directory called Home Jocan ROS. But you can name your workspace whatever you like and store the directory anywhere in your account that you prefer. Use the normal make directory command to create a directory. Refer to this new directory as your workspace directory. For many users, there's no real need to use more than one ROS workspace. However, ROS Catkin build system, which was introduced in section 3.2.2, attempts to build all of the packages in a workspace at once. Therefore, if you're working on many packages or have several distinct projects, it may be useful to obtain several independent workspaces. One final step is to set up the workspace. Create a subdirectory called source inside the workspace directory. As you might guess, this subdirectory will contain the source code for your packages. Creating a package, the command to create a new ROS package, which should be run from the source directory of your workspace, looks like this. Catkin create package name. Actually, this package creation command doesn't do much. It creates a directory to hold the package and creates 2 configuration files inside that directory. The first configuration file called package.xml is the manifest discussed in section 2.4. The second file called cmakelist is a script for industrial strength cross-platform build called cmake. It contains a list of build instructions, including what executables should be created, what source files to use to build each of them, and where to find the include and libraries needed for those executables. CMake is used entirely by Catkin. In the comment sections, we'll see a few edits you'll need to make to each of these files to configure your new package. For now, it's enough to understand that Catkin create packages doesn't do anything magical. Its job is to simply make things a bit more convenient by creating both the package directory and default version of these 2 config files. This 3-layered directory structure or workspace directory called a source directory containing a package directory might seem to be overkill for simple projects and small workspaces, but the Catkin build system requires it. ROS package names following a naming convention that allow only lowercase letter, digits, and underscores. The convention also requires that the first character be a lowercase letter. A few ROS tools, including Catkill, will complain about packages that do not follow this convention. All of the examples in this book belong to a package called AGITR, named after the initials of the book's title. If you like to recreate this package yourself, you can create a package within this name running this command from your workspace source directory. Catkin create package AGITR. An alternative to creating the AGITR package yourself is to download the archive of this package from the book's website and expand it from within your workspace directory. Editing the manifest. After creating your package, you may want to edit it in a package.xml, which contains some metadata describing the package. The default version is installed by Catkin create package, is liberally commented and largely self-explanatory. Note, however, that most of this information is not utilized by ROS, neither at the build time nor at the runtime, and only becomes really important if you release your package publicly. In the spirit of keeping documentation in sync with actual functionality, a reasonable minimum might be able to fill in the description of maintainer fields. Listings 3.1 shows the manifest from our AGITR package. 3.2 Hello ROS. Now that we've created a package, we can start writing ROS programs. A simple program listing 3.2 shows a ROS version of the canonical Hello World program. Canonical? Canonical. I can't say that word. This source file named hello.tpp belongs in your package folder, right next to package.xml and cmakelist.txt. Some online tutorials suggest creating a source directory within your package directory to contain C++ source file. This additional organization might be helpful, especially for larger packages with many types of files, but it isn't strictly necessary. We'll see how to compile and run this program momentarily, but first let's examine the code itself. The header file, the ROS.h, includes declarations of the standard ROS classes. You'll want to include it in every ROS program that you write. The ROS : init function initializes the ROS client library. Call this once at the beginning of your program. The last parameter is a string containing the default name of your node. This default name can be overridden by a launch file or by a ROS run command line parameter. The ROS node handle object is the main mechanism that your program will use to interact with the ROS system. Creating this object registers your program as a node with the ROS master. The simplest technique is to create a single node handle object to use throughout the program. Internally, the node handle class maintains a reference count and only registers a new node within the master when the first node handle object is created. Likewise, the node is only unregistered when all of the node handle objects have been destroyed. This detail has two impacts. First, you can, if preferred, create multiple node handles objects, all of which refer to the same node. There are occasionally reasons that this would make sense. An example one situation appears on page 129. Second, this means that it is not possible using the standard ROS CPP interface to run multiple sync nodes within a single program. The ROS info stream line generates an informational message. This message is sent to several different locations, including the console screen. We'll see more details about this kind of log message in Chapter 4. Compiling the hello program. How can you compile and run this program? This is handled by ROS build system called Catkin. There are 4 steps. Declaring dependencies. First, we need to declare the other packages in which ours depends. For a C++ program, this step is needed primarily to ensure the Catkin provides the C++ compiler with the appropriate flags to locate the header files and libraries that it needs. To list dependencies, edit the cmakelist.txt in your package directory. The default version of this file of this line is find_package catkin require. Dependencies on other catkin packages can be added in component sections on this line. Find package catkin required components, package names. For the hello example, we need one dependency on a package called ROS CPP, which provides the C++ ROS client library. The required find package line, therefore, is find package _ catkin required components ROS CPP. We should also list dependencies in package manifest package.xml using the build depend and run depend elements. Build _depends, package name, close build _depend, run _depend, package name, close run _depend. In our example, the hello program needs ROS CPP, both at the build times and at the run times. So the manifest should contain build depend ROS CPP, close ROS, close build depend, open run depend, ROS CPP, close run _depend. However, dependencies declared in the manifest are not used in the build process. If you omit them here, you will likely won't see any errors and error messages until you distribute your package just to others who try to build it with having the required packages installed. Declaring an executable. Next, we need to add 2 lines to the cmakelist.txt declaring the executable we would like to create. The general form is add _executable, executable name source files, and target link libraries, executable name, catkin libraries. The first line declares the name of the executable we want and a list of source files that should be combined to form that executable. If you have more than one source file, list them all here, separated by spaces. The second line tells CMake to use appropriate library flags, defined by the find _package line above. When linking its executable, if your package contains more than one executable, copy and modify these 2 lines for each executable you have. In our example, we want an executable called hello, compiled from a single source file called hello CPP. So we would add these lines to cmakelist.txt. Add executable hello.cpp, target link libraries hello catkin library. For reference, listing 3.3 shows a short cmakelist.txt that suffices for our example. The default version of cmakelist.txt created by CAD can create package contains some commented out guidance for a few other purposes. For many simple programs, something similar to the simple version shows here is enough. Building the workspace. Once your cmakelist.txt is set up, you can build your workspace, including compiling all of executables and all of its packages using this command, catkin_make, because it is designed to build all the packages in your workspace. This command must be run from your workspace directory. It will perform several configuration steps, especially the first time you run it, and create subdirectories called devel and build with your workspace. These two new directories contain build related files like automatically generated make files, object code, and the executable themselves. If you like, the develop and build subdirectories can safely be deleted when you finish working on your package. If there are compile errors, you'll see them here. After correcting them, you can make again to complete the build process. If you see errors from the make that the header ROS, ROS.h cannot be found, or undefined reference errors on ROS.init or other ROS functions, the most likely reason is that your CMake list text does not correctly declare dependency on ROS CPP. Sourcing setup.bash. The final step is to execute a script called setup.bash, which is created by make inside the devel subdirectory of your workspace. Source devel /setup.bash. This automatically generated script sets several environmental variables that enable ROS to find your package and its newly generated executable. It is analogous to the global setup.bash from section 2.2, but tailored specifically to your workspace. Unless the directory structure changes, you only need to do this only once in each terminal, even if you modify the code and recompile with make. Executing the hello program. When all of those build steps are complete, your new ROS program is ready to execute using ROS run section 2.6. Just like any other ROS program in our example, the command is ROS run agitr hello. The program should produce output that looks something like this. Hello, ROS. Don't forget to start ROS score first. This program is a node, and nodes need a master to run correctly. By the way, the numbers in this input line represent time, measured in seconds since January 1st, 1970, when our ROS info stream line was executed. This ROS run, along with some other ROS commands, may generate an error that looks like ROS pack, error stack packages, package name not found. Two common causes of this error: misspelling the package name and failing to run the setup.bash for your workspace. 3.3 A Publisher Program. The Hello program from the previous section showed how to compile and run a simple ROS program. That program was useful to an introduction to Gatkin, but like all Hello World programs, it didn't do anything useful. In this section, we'll look at a program that interacts with ROS a bit more. Specifically, we'll see how to send randomly generated velocity commands to a turtlesome turtle, causing it to wander aimlessly. The brief C++ source code for the program is called pub_bell. Appears as listings 3.4. This program shows all of the elements needed to publish a message from the code. The main differences between pub_bell and hello all stem from the need to publish messages, including the message type declaration. You'll likely recall from section 2.7.2 that every ROS topic is associated with a message type. Each message type has a corresponding C++ header file. You need to include this header for every message type used in your program with a code like this. #include package name, type name, .header. Note that the package name should be name of the package containing the message type and not necessarily the name of your own package. In pub_bell, we want to publish messages of type geometry messages, type name twist owned by package name geometry messages. So we need this line. #include geometry messages twist.h. The purpose of this header is to define a C++ class that has the same data members as the field of this given type. This class is defined in a namespace named after the package. The practical impact of this naming is that when referring to merge message classes in C++ code, use the double colon, also called the scope resolution operator. To separate the package name from the type name in our pub_bell example, the header defines a class called geometry messages : twist. Creating a publisher object. The work of actually publishing the message is done by an object class, ROS publisher. A line like this creates the object we need ROS publisher pub equals node handler advertiser, message type, topic name, queue size. Let's have a look at each part of this line. The node handled is an object of class ROS node handle. Once that you created near the start of your program, we're calling the advertise method of the object. The message type part inside of the angle bracket from the called the template parameter is the data type for new messages we want to publish. This should be the name of the class defined if the header discussed above. In the example, we use the geometry messages twist class. The topic name is a string containing the name of the topic on which we want to publish it. It should match the topic name shown by the ROS topic list or the RQT graph, but usually without the leading slash. We drop the leading slash to make sure the topic named a relative name. Chapter 5 explains the mechanics and purposes of relative names. In the example, the topic name is turtle1 command velocity. Be careful about the difference between topic name and message type. If you accidentally swap these two, you'll get lots of potentially confusing compile errors. The last parameter to advertise is an integer representing the size of a message queue for this publisher. In most cases, a reasonable large value, say 1,000, is suitable if your program rapidly publishes more messages than the queue can hold. The oldest unset messages will be discarded. This parameter is needed because in most cases, the messages must be transmitted to another node. This communication process can be time-consuming, especially compared to the time needed to create messages. ROS mitigates this delay by having the publish method, see below, store the message in a nutbox queue, and return right away. A separate thread behind the scenes actually transmits in the message. The integer value given here is the number of messages and not, as you might guess, the number of bytes that the message queue can hold. Interestingly, the ROS client library is smart enough to know when the publisher and subscriber nodes are part of the same underlying process. In these cases, the message is delivered directly to the subscribers without using any network transport. This feature is very important for making nodelets, that is, multiple nodes that can be dynamically loaded into a single process, efficient. If you want to publish messages on multiple topics from the same node, you'll need to create a separate ROS publisher object for each object. Be mindful of the lifetime of your ROS publisher objects. Creating the publisher is an expensive operation, so it's usually a bad idea to create a new ROS publisher object each time you want to publish a message. Instead, create one publisher for each topic and use that publisher throughout the execution of your program in pub-vel. We accomplish this by declaring the publisher outside of the while loop. Creating and filling in the message object. Next, we create the message object itself. We already referred to the message class when we created the ROS publisher object. Objects of that class have one publicly accessible data member for each field in the underlying message type. We use ROS message show to see that the geometry messages twist messages has two level fields, linear and angular, each one which contains 3 subfields, x, y, and z. Each of these subfields is a 64-bit floating point number called a double by most C++ compilers. The code is listing 3.4 creates a geometry messages twist object and assigns a pseudo-random numbers to the 2 of these data members, geometry messages, twist message, message linear x, and double random x, message angular z, and 2 times double random / double random x -1. This code sets the linear velocity to a number between 0 and 1, and the angular velocity is a number between -1 and 1. Because TurtleSim ignores the other 4 fields, message linear z, message angular x, and message angular y, we leave them with their default value, which happens to be 0. Of course, most messages types have fields with types of other than float64. Unfortunately, the mapping from ROS fields types to C++ types works precisely the way you might expect. One fact that may not be obvious is that the fields and array types shown within square brackets by ROS message show are realized as STL vectors in C++ code. Hello? Chapter 3, continuing publishing the message. After all of that preliminary work, it is very simple to actually publish the message. Using the publish message of the ROS publisher object, in the example, it looks like this. Pub.publish parentheses message. This method adds the given message, the publishers.go message queue from it, which will be sent as soon as possible to any subscribers of the corresponding topic. Formatting the output. Although it's not directly related to publishing our velocity commands, the ROS info stream line in listing 3.4 is worth a look. This is a more complete illustration of what ROS info stream can do, because it shows the ability to insert data other than strings, in this case, the specific randomly generated message fields, into the output. Section 4.3 has more information about how ROS info stream works. 3.3.2 The publishing loop. The previous section covered the details of message publishing. Our pubvel example repeats the publishing steps inside a while loop to publish many different messages as time passes. The program uses two additional constructs to form this loop. Checking for node shutdown. The condition of pubvel's while loop is ROS : OK parentheses. Informally, this function checks whether our program is still in good standing as a ROS node. It will return true until the node has some reason to shut down. There are a few ways to get ROS OK to return false. You can use ROS node kill on the node. You can send an interrupt signal Control-C to the program. Interestingly, ROS init installs a handler for the signal and uses it to initiate a graceful shutdown. The impact is that Control-C can be used to make ROS OK return false, but does not immediately terminate the program. This can be important if there are cleanup steps, writing log files, save and partial results, saying goodbye, etc. That should happen before the program exits. You can call somewhere in the program itself, ROS shutdown. This function can be useful to signal that your node works is complete from deep within your code. You can start another node with the same name. This usually happens if you start a new instance of the same program. Controlling the publishing rate. The last new element of pubvel is it uses of ROS rate object. ROS : rate parentheses 2. This object controls how rapidly the loop runs. The parameter in its constructor is in units of hertz, that is, in cycles per second. This example creates a rate object designed to regulate a loop that executes 2 iterations per second. Near the end of each loop iteration, we call this the sleep method of this object, rate.sleep. Each call to this method causes a delay in the program. The duration of delay is calculated to prevent the loop from iterating faster than the specified rate. Without this kind of control, the program would publish messages as fast as the computer allows, which can overwhelm publish and subscribe queues and waste computation and network resources. On the author's computer, an unregulated version of this program topped out around 6,300 messages per second. You can confirm that this regulation is working correctly using ROS topic hertz or pubvel. The results should look similar to this. Average rate 2.0, min 0.5 seconds max, standard deviation 0.5 seconds, 0.00006 seconds, window 10. We can see that messages are being published at a rate of 2 per second with very little deviation from this schedule. You might be thinking of an alternative to ROS rate that uses a simple fixed delay, perhaps generated by sleep or use sleep in each loop iteration. The advantage of ROS rate object over this approach is that ROS rate can account for the time consumed by other parts of the loop. If there's a non-trivial computation to be done in each iteration, as we would expect from a real program, the time consumed by this computation is subtracted from the delay. In extreme cases in which the real loop takes longer than the requested rate, the delay induced by sleep can be reduced to 0. Compiling pubvel. The process of building pubvel is mostly the same as for hello. Modify cmakelist.txt and package.xml, and then use CAD can make to build your workspace. There is, however, one important difference from hello. Declaring messages type dependencies. Because pubvel uses a message type from the geometry message package, we must declare a dependency on the package. This takes the same form as the ROS CPP dependency discussed in section 3.2.2. Specifically, we must modify the find package line in cmakelist to mention geometry message in addition to ROS CPP. Find underscore package, CAD can require components, ROS CPP, geometry messages. Note that we're modifying the existing find package line rather than creating a new one. In the package XML, we should add elements for new dependencies. If you skip or forget the step, then CAD can make may not be able to find the header geometry message twist.h. When you see errors about missing header files, it is a good idea to verify the dependencies of your package. Section 3.3.4, executing pub-bell. At last, ready to run pub-bell. As usual, ROS run can do the job. ROS run at AGITR pub-bell. You also want to run a turtle sim simulator so that you can use the turtle to respond to the motion commands that pub-bell publishes. ROS run turtle sim node, figure 3.1 shows an example of the results. In figure 3.1, turtle sim turtle responding to random velocity commands from pub-bell. Section 3.4, a subscriber program. So far, we've seen an example program that publishes messages. This is, of course, only half of the story when it comes to communicating with other nodes via messages. Let's take a look now at the program that subscribes to the messages published by other nodes. Continuing to use TurtleSim as a test platform, we'll subscribe to Turtle1 pose topic on which TurtleSim nodes publishes. Messages on this topic describe the pose, a term referring to the position and orientation of the turtle. Listing 3.5 shows a short program that subscribes to those messages and summarizes them for use for us via ROS info stream. Although some parts of the program should be familiar by now, there are 3 new elements. Writing a callback function. One important difference between publishing and subscribing is that a subscriber node doesn't know when the messages will arrive. To deal with this fact, we must place any code that responds to incoming message inside a callback function, which ROS calls once for each arriving message. A subscriber callback function looks like this: void function name, const package name, type name, and message. The package name and type name are the same as for publishing. They refer to the message class for the topic to which we plan to subscribe. The body of the callback function that has access to all of the fields in the received message and can store, use, or discard data as it sees fits. As always, we must include the appropriate header that defines this class. In the example, our callback accepts messages of type turtlesim pose, so the header we need in turtlesim pose.h. We can learn that this is the correct message type by using ROS topic info. Recall section 2.7.2. Callback simply prints out some data from the messages, including its X, Y, and data members via ROS info stream. We can learn what data fields the message type has using ROS message show. Again, from section 2.7.2. A real-world program would, of course, generally do some meaningful work with the message. Notice that the subscriber callback functions have a void return type. A bit of thought should confirm that this makes sense. Since it's ROS's job to call this function, there's no place in a program for any non-void return values to go. Creating a subscriber object. To subscribe to the topic, we create a ROS subscriber object. ROS : subscriber sub equals node handler dot subscribe. Topic name, queue size, pointer to a callback function. This line has several moving parts, most of which have analogous in the declaration of ROS publisher. The node handle is the same node handle object that we've seen several times already. The topic name is the name of the topic to which we want to subscribe in the form of a string. This example uses turtle1 pose. Again, we omit the leading slash to make this string a relative name. The queue size is the integer size of the message queue for this subscriber. Usually, you can have a large value like 1,000 without worrying too much about the queuing process. When new messages arrive, they are stored in a queue until ROS gets a chance to execute your callback function. This parameter establishes a maximum number of messages that ROS will store in that queue at one time. If new messages arrive when the queue is full, and the oldest unprocessed messages will be dropped to make room. This may seem on the surface to be very similar to the technique used for publishing a message, see page 50, but differs in an important way. The rate at which ROS can empty a publisher queue depends on the time taken to actually transmit the messages to subscribers is largely out of control. In contrast, the speed with which ROS empties a subscribing queue depends on how quickly we process callbacks. Thus, we can reduce the likelihood of a subscriber queue overflowing by ensuring that we allow callbacks to occur via ROS spin or ROS spin once frequently, and B, reducing the amount of time consumed by each callback. The last parameter is a pointer to the callback function that ROS should execute when messages arrive. In C++, you can get a pointer to a function using the ampersand @resolve operator on the function name. In our example, it looks like this: ampersand pose message received. Don't make the common mistake of writing parentheses or even message after the function name. Those parentheses and arguments are needed only when you actually want to call a function. Now you only want to get a pointer to a function without calling it, as we're doing here. ROS applies the required arguments when it calls your callback function. Comment on C++ syntax. The ampersand is actually optional, and many programs omit it. The compiler can tell you what you want to point to the function rather than the value returned from the executing function, because the function name is not followed by parentheses. The author's suggestion is to include it, because it makes the fact that we're dealing with a pointer more obvious to human readers. You might notice that while creating a ROS subscriber object, we do not explicitly mention the message type anywhere. In fact, the subscribe method is templated, and the C++ compiler infers from the correct message type based on the data type of the callback function pointer we provide. If you use the wrong message type as the argument to your callback function, the compiler will not be able to detect this error. Instead, you'll see a runtime error message complaining about the type mismatch. These errors could depend on the timing, come from either the publisher or subscriber nodes. One potentially counterintuitive fact about ROS subscriber objects is that it is quite rare to actually call any of their methods. Instead, the lifetime of the object is the most relevant part. When we construct a ROS subscriber, our nodes establish connections with any publishers of the named topic. When the object is destroyed, either by getting out of scope or by a delete of an object created by the new operator, those connections are dropped. Giving ROS control. The final complication is that ROS will only execute our callback function when we give it explicit permission to do so. There are actually two slightly different ways to accomplish this. One version looks like this: ROS spin once parentheses. This code asks ROS to execute all the pending callbacks from all the node subscriptions and then return control back to us. The other option looks like this: ROS spin. This alternative to ROS spin once asks ROS to wait for and execute callbacks until the node shuts down. In other words, ROS spin is roughly equivalent to this loop, while ROS OK, ROS spin once. The question of whether to use ROS spin once or ROS spin comes down to this: does your program have any repetitive work to do other than responding to callbacks? If the answer is no, then use ROS spin. If the answer is yes, then a reasonable option is to write a loop that does the other work and calls ROS spins once periodically to the process callbacks. Listing 3.5 uses ROS spin because that program's only job is to receive and summarize incoming post messages. A common error in subscriber programs is to mistakenly omit both ROS spin once and ROS spin. In this case, ROS never has an opportunity to execute your callback function. Omitting ROS spin will likely cause your program to exit shortly after it starts. Omitting ROS spin once might make it appear as though no messages are being received. 3.4.1 Compiling and executing subpose. This program can be compiled and executed just like the first two examples we've seen. Don't forget to ensure that your package has a dependency on TurtleSim, which is needed because we're using the TurtleSim post message type. See section 3.3.3 for a reminder of how to declare this dependency. A sample of the program's output from when both TurtleSim node and pubvel were also running appears as listing 3.6. 3.5, looking forward. This chapter's intent was to show how to write, compile, and execute a few simple programs, including programs that perform the core ROS operation of publishing and subscribing. Each of these programs use a macro called ROS info stream to generate informational log messages. In the next chapter, we'll examine ROS login system, of which ROS info stream is just a small part more completely.